Right. Hey everyone, welcome to the August Bay Area Rust Meetup. As always, thanks Mozilla for food and space and everything. A couple of quick announcements. The survey as of today is up. Please fill it in. This year we've actually translated it in a bunch of languages too, so choose a language that you're most comfortable in and fill it in. It's on the blog. Anyone going to RustConf? Woo! Significant. All right, see you there. Yeah, next meetup will probably be in September in probably Stanford again. I don't think we have a date yet, but yeah. Today we have two speakers. We have Stephen Heidel from Rigetti, a quantum computing company, talking about controlling a quantum computer with code. This is less rusty, but we'll get into how they plan on using Rust, so it should still be interesting. And then we have Isaac Goldberg from Dropbox on Rust features and randomized testing. All right.
Thanks. Great. Hello, everyone. I made sure to use Firefox for this presentation. Actually, I was a long-time Chrome user until about 6 months ago when the newest Mozilla, or the newest Firefox came out, which was faster and better and seems like not stealing all my data. So that seemed, more ideal. And since then, I've been pretty happy with it. And presentation works great. So, and it's what? Oh yeah, it's called Quantum. Oh, I didn't even. Whoa. So I'm going to talk about a different type of quantum, quantum computing. So this talk is going to be, I guess, a little different than some of the standard Rust meetup talks in that it's 98% talking about quantum computing, giving you an introduction to it, and also telling you some of the software that runs behind the scenes. And then I'll kind of mention at the end a little bit about the story of the software that we've been writing, how it's currently being written in Python, and how we're exploring Rust as an option to deal with some of our performance issues. So with that, I will get started talking about some of the software behind quantum computers. So if I found my mouse, there it is, great. So in the early 1900s, physicists began to observe something interesting. They saw some strange behaviors that they didn't quite understand, particles that acted like waves, and particles that didn't appear to be in one fixed position at one time. So that was a little odd, but over the course of the 20th century, these observations have been refined into a coherent theory of quantum mechanics that has been very successful in explaining our physical reality. So this is despite the fact that quantum mechanics remains very difficult to grasp, and that many of the strange properties that happen at that scale do not happen at the macroscopic scale we're used to. So fast forward now to 1982, and the physicist Richard Feynman speculated that some of these quantum mechanical properties might be useful for doing computation. If you draw an analogy to classical computers at the 1850s, 150 years ago, they came up with the laws of electricity, and it was about 100 years later, almost similar to quantum computing, that they decided that that would be a good medium for doing computation. So the same thing is happening here. Feynman speculated that in 1982. 1994, 12 years later, a professor at MIT named Peter Shor came up with an algorithm that was provably faster to run on a quantum computer than on a classical computer. And that was to factor prime numbers. So now basically the stage was set. We had the idea and we had an algorithm that would perform better. So now the only question was, can we actually build one? And fortunately, today I'm excited to say that quantum computing has moved from the realm of academia into the realm of engineering. So it is indeed possible to create a quantum computer, just like the ones theorized by Feynman 3 decades ago. And that's exactly what my company, Rigetti Computing, does. That could have been timed better. So Rigetti Computing is a full-stack quantum computing company. And when I say full stack, I don't just mean full stack in the sense the front-end, back-end engineer. I mean in the sense that we build the hardware, the software, the control systems, and the silicon, and everything needed to do quantum computing. So here's some pictures of our lab in Berkeley. This is 2 of our quantum computers. We have a fleet of them. Some of them are deployed to the cloud and are publicly accessible. The thing you're looking at here is basically the insides of a dilution refrigerator, which is used to cool a quantum chip down to just above absolute zero, about 30 millikelvin. And that's temperatures required for some sort of quantum properties to be useful. And this is our fabrication facility in Fremont. So we built this facility from scratch. We think it's the only one in the world that specializes in just producing superconducting quantum chips. And I actually brought one with me today to use as a presentation gimmick. So here it is. Whoa, a quantum computer. So this is a chip that was manufactured in Fremont by Rigetti, and it contains 8 qubits on it. So a lot of, the quantum mechanics is very new and novel, but there are some things about this chip that are very familiar for people who are used to doing computation. Namely, it's printed on silicon, it's manufactured using traditional engineering processes or fabrication processes, and the only difference really is that the computers that you have in your laptop are semiconducting, and in this case, this one becomes superconducting when you cool it down to those really close to zero, absolute zero temperatures. I'm going to put this away because if I lose this, the introduction to my talk will be, hello, I'm Stephen, and I used to work at Rigetti Computing. So I'm going to keep an eye on that, but we can continue. So as exciting as this device is, and as exciting as our fabrication facility is, I'm a software engineer. This is a software, people who are interested in software, interested in Rust, so I'm not here to talk about silicon, I'm here to talk about software. And in particular, I want to talk about all the software engineering that happens behind the scenes in actually getting these quantum computers to work. So my personal background is that I was a software engineer for 3 years working at LinkedIn, doing enterprise cloud services. And that tends to be a little different than most of my colleagues who have PhDs in physics or came from big universities and so forth. Quantum computing, though, is a multidisciplinary effort. It requires people that are good at fabrication, good at hardware, and of course, good at software. So I hope that by the end of this talk, you'll kind of get a sense of all the new and innovative software that's needed in order to build a quantum computing system, and in particular, why it's important for that software to be very performant. So before I get into that, though, no good quantum computing talk is complete without explaining first just what the heck is a quantum computer. And so that's where we'll start. And then I'll move on to looking at some of the software that runs behind the scenes. So what is a quantum computer? I'm sure you're all intimately familiar with the bit. A bit can encode a single piece of binary information, a 1 or a 0, which I'm representing here with up and down arrows. So to represent more information, we simply have to add more bits. The storage and manipulation of bits is the foundation of classical computing. Quantum computers, on the other hand, use a different fundamental object called the qubit. Like a bit, qubits can have a 0 and a 1 state. I've placed the arrow in a 3-dimensional unit sphere because a qubit can also be in other intermediate states along the surface of the sphere. For instance, a qubit could be in this right-facing state, which is neither strictly 0 nor strictly 1. And we call these weird intermediate states superposition states. Knowing nothing else, this provides us our first hint that there may be some advantage to working with qubits over bits. So classical bits can only store one bit of information, whereas to know the full state of the qubit, you'd have to understand its real coordinates along the sphere. So superposition is one key feature of quantum mechanics that we can take advantage of. And there's also another very useful feature called entanglement. So here's an analogy to explain entanglement. Imagine you had two buckets, and you placed inside these buckets the numbers 0 and 1. Now if we were to randomly select one number from each bucket, there's a 25% chance of each of the following outcomes occurring. So either 0, 0, 0, 1, 1, 0, 1, 1. So if, however, these buckets were entangled in a certain way, then something different would happen. If 0 was selected from the left bucket, then you would also be guaranteed to select a 0 from the right bucket, and similarly for 1s. So there's 50-50 chance of getting either 0, 0 or 1, 1, and 0% chance of getting the others. This is a strange property. Despite the fact that you're picking randomly from each bucket, you're still always guaranteed to get the same number. So entanglement is a strange phenomenon wherein qubits become associated with each other in a special way. And the only way you can fully understand a quantum mechanical system is to understand it as a whole, not as at the individual qubit level. So earlier I showed you how you can store more information in a single bit, a single qubit, than in an individual bit. And now we can make an additional observation, which is that there's also relationships, information stored in the relationships between qubits. So to fully understand an arbitrary quantum state, we'd also need to know the positions of each qubit, but also how they are related to each other. Every qubit could possibly become entangled with every other qubit, forming a fully connected graph. So when you increase the number of qubits, you exponentially increase the amount of information that's needed to represent the quantum state. We can simulate quantum computers using the computers we have today, but due to this exponential scaling of information, it becomes very difficult very quickly. So any modern laptop, including mine, can simulate a quantum computer of about up to 26 qubits. To simulate 36 qubits, you'd need an expensive server with at least 1 terabyte of memory. And at 46, this requires the help of a massively parallel supercomputer with a lot more memory. So every time you add an additional qubit, it multiplies the difficulty level such that it isn't very much longer at 60 qubits that you'd basically need all the computers in order to fully simulate a quantum computer of that size. So at this point, people tend to get really excited about quantum computing. It seems like a given that given this exponential scaling of information, this would allow us to solve problems that were previously thought to be impossible. Unfortunately, though, it's not quite that easy. So there's a couple things that get in the way of easily coming up with this exponential scaling. So the first is that while the quantum computers can store an exponential amount of information, you can only extract a finite amount of it through measurement. When you measure a qubit that's in some intermediate state between 0 and 1, most of the information about where it was before you measured it is lost. The qubit will collapse to either a 0 or a 1 state randomly, depending on how close it was to either the North Pole or the South Pole of the sphere. So for instance, in this example, the qubit being on the equator means that there's a 50% chance of it being in the 0 state and a 50% chance of it being in the 1 state. Taking another example, in this case the qubit is closer to the North Pole, meaning there's a higher chance of observing it in the 0 state than there is of observing it in the 1 state. But when we measure it, we've lost all the information about the relative position of the qubit, and we've also lost information about its rotation around the x-axis. So a qubit that's pointing right is going to have the same probability distribution as a qubit that's pointing left. When we work with a quantum computer, we put in a finite amount of information. Then, during the computation, the qubits can be in very rich intermediate states. But once we get around to extracting the answer from our programs, we only get a finite amount of information back out. So So clever people thought maybe they could come up with a solution to this, which was if they simply had an operation that could clone the state of a qubit, then we could make many copies of it and measure it many times. And based on this sampling, you could get some information back about where the qubit was on the sphere. This seems like a great workaround that would allow us to extract an arbitrary amount of information from the computer. Unfortunately, however, such an operation does not exist and is actually prohibited by the laws of quantum mechanics. So that's not ideal. At this point, it may seem like the only good that quantum computers will give us is in the generation of random numbers, which indeed this is a great use case for quantum computers. The other day I was trying to decide between a grapefruit LaCroix and just a regular LaCroix, and so sent a coin flip operation to the quantum computer and it came back. But that type of business application doesn't really justify the fact that we've had $100 million worth of investment. Fortunately, there is some good news, which is there are useful applications that you can come up with despite these limitations. And people have come up with a number of creative ideas on how they can use the qubits' interactions with each other during this intermediate state to affect better algorithms and more useful algorithms than just random numbers. For instance, one can engineer a quantum state where wrong answers will cancel each other out, leaving you with a high probability of measuring the correct answer when you eventually get to the end of your program. A basic application of this can be found in Grover's search algorithm. So in a search algorithm, we are looking for a single solution in a large state space of possible solutions. Classically, the best performance you could achieve would be to try every possible input to the function until you find the right one. So if you had n possible inputs, then you'd reach the solution in at most n applications of the function. Quantum computers, though, can do better. Grover's algorithm works like this. First, you place the quantum computer in a superposition such that all inputs are equally likely to be measured. Then you repeatedly apply your function in a special way such that it increases the probability of the right answer being measured while slowly canceling out the wrong answers. And it's been proven that you can measure the right answer with high probability in at most square root n steps, which is a major improvement over simply guessing and checking every possible input like in a classical computer. The other thing that quantum computers could be really good at is in simulating quantum systems. So quantum systems such as molecules, for instance, are much easier to map to a quantum computer than mapping to a classical computer. So at Rigetti, here are some results that we ran on our quantum computer to simulate the bond dissociation energy of the molecule H2, and you see the results in this graph. The blue line is what the theory predicted, and then when we simulated it on our quantum computer, QPU, or quantum processing unit, we ended up with a shape that looks similar to what the theory expected us to get. So molecules of this size are not that interesting, but this shows quantum computing has potential in the future to simulate and understand chemical problems that are currently beyond our computational grasp. All right, so hopefully everyone is now a quantum computing expert. Of course, we really only scratched the surface of what's possible with a quantum computer, but I do want to switch gears and take you behind the scenes to what's needed to realize the execution of a quantum program. So like I kind of mentioned at the beginning, keep an eye out for some of the new and innovative software that's required for this to work. At this point, it should not surprise you that programming a quantum computer is very different than programming a classical computer. We need to use a specialized quantum programming language. And the language that we use is called QUIL, which is short for Quantum Instruction Language. QUIL looks very similar to assembly code. It's a step-by-step list of operations that should be executed on particular qubits. So on the left, you can see some examples of the types of instructions that you'd run on a quantum program. For instance, an X operation rotates the qubit by 180 degrees. The H instruction rotates the qubit halfway, which is useful for putting qubits into the superposition states. And there are also multiple operations that operate on multiple qubits, such as the C naught, which can take any two qubits and place them into an entangled state. At the end of every quantum program, you append measure instructions, which read out a single bit of classical information and place them in a classical register. Quill also includes some other instructions for doing basic assembly language like tasks, such as branching and jumps, which you'd be familiar with if you know anything about assembly. So step one of executing a quantum program is to convert it into this format. So the Quill program is then packaged up and sent to our offices in Berkeley over the cloud. And beside every quantum computer, there's a regular old classical computer that we call the control computer, and it has a number of tasks it needs to perform before we can physically realize the quantum program that you want to run. So the first of these tasks is compilation. So to explain what a quantum compiler does, I'll explain it by drawing an analogy to something we may be more familiar with, which is how Rust gets compiled. So if you take Rust as an example, Rust eventually compiles into LLVM, and the compiler itself is written in Rust. So another way of saying this is that the source language is Rust, the target language is some intermediate representation, and the compiler itself is written in Rust. In our case, our quantum compiler takes in Quill, the quantum instruction language, as input, and compiles it to a subset of Quill called protoQuill. So there are an infinite number of possible quantum operations that you could perform on a qubit. However, our computers can only perform a small subset of these. Fortunately, though, there's sort of a universal gate set that, provided you have a certain minimum threshold of operations that you can perform, then you can also perform all the operations as they get reduced by the compiler. So you can sort of think of this like CPU architectures, where different CPU architectures support different types of assembly. An Intel would be a little bit different than an AMD processor, for instance, but they're all universal. And that's the same with our quantum computers. We have different varieties, but at the end of the day, they can all support the high-level quantum instruction language. So our compiler runs on a classical computer and is written in Lisp, which has, because much of what the compiler does is symbolic manipulations of quantum programs through linear algebra and through basically various almost trigonometric identities to reduce one gate set to another gate set. Here's some examples of some of the reductions that I've described earlier. You can take longer quantum programs and turn them into shorter ones that are equivalent using a number of different rules. And this is basically just like machine learning and exercise in linear algebra. Each of these qubit operations can be represented as a matrix operator, and then you take various decomposition rules to transform operators from one set into another. So another challenge that the compiler has to solve is dealing with limited connectivity of qubits. So in Quill, you can perform a 2-qubit operation on any arbitrary pair, but in reality, the quantum devices that we manufacture do not form a fully connected graph. So here is a picture of our 20-qubit device. The little groups of 3 circles all together form 1 qubit. You can sort of see a zoomed-in picture there. This whole picture is about the size of a thumbnail, like a human thumbnail, a computer thumbnail. So, yeah, the qubits are quite small. But anyways, the point here is that each qubit is connected to no more than 3 of its neighbors. And some of the qubits on the edge, the fringes, are connected to even fewer than that. So the compiler has to deal with this. If we take the same picture again in graph form, let's say we wanted to perform an operation on qubits 1 and 10. 1 and 10 are not connected, but fortunately the compiler can take advantage of a swap operation to swap the quantum state around and move the quantum state from 10 to 6 such that you can now perform a 2-qubit operation on 1 and 6. So the compiler has both this optimization problem to solve, which I mentioned earlier, and then also a very interesting and difficult graph theory problem in order to make our quantum programs efficient. So once all this happens, we can move on to the next step, which is to convert the abstract instructions into something that is physical. So our quantum computers, like this one, respond to bundles of photons that are sent to it through pulse generators. And the pulse program is a sequence of these pulses. If we continue my compiler analogy from earlier a little further, most compilers usually have multiple steps. So the next step after some IR is to then take that and turn it into native machine instructions. For the quantum computing side, our next step is to take protoquil and turn it into a pulse program. And we currently do that with Python, but I'll get to that later. So let's say the qubit is in a 0 state. To flip it to the 1 state, we need to send an X instruction. But that instruction on its own has no meaning to the quantum computer. The pulse is what will actually cause the quantum mechanical interaction necessary to perform the operation. So we send this pulse to when we send this pulse to the qubit, it responds by flipping its state. So take a moment now to really consider how this differs from classical computing. In a classical computer, you have a CPU which has on it the various accumulators and circuits necessary for performing different types of computations. You then send the data through the CPU. So this is the opposite of a quantum computer. In a quantum computer, the data is what stays on the chip, and you send in the program through these pulses. Different types of instruction require different shapes of pulses to execute. So for instance, by varying the length of the pulse, you can control how far on the sphere the qubit moves. With a short pulse, it may only go a quarter of the way, but with a longer one, you could flip it all the way around its axis. So these pulse programs sort of look like musical scores. You need to know exactly which notes to play, when to play them, and how long to play them for. And this gets us to the real crux of the difficulty of building a quantum computer, or at least building the software that runs a quantum computer, and that all these parameters are analog parameters. Quantum computers are inherently analog devices. They are not digital like classical computers with a 0 and 1 state. Instead, everything sort of lives in a gray area where you can never reach 100% accuracy with the operations that you're performing. There are a number of analog variables to adjust. For each pulse you play, you have a number of knobs that you can adjust, such as width, height, and frequency. You can imagine how this would be a challenge for the software to find these numbers. Every parameter is a continuous variable, and performing highly accurate numerical calculations on each of these parameters is incredibly important. And if this weren't already hard enough, the other problem is that these parameters are not fixed. So various changes to the computer's environment, the temperature, even the temperature of the office, can create noise and affect the quantum computer's operation. So that means the system has to constantly be undergoing recalibration in order to find the right parameters depending on the environment. There's an enormous amount of data being collected every day about our quantum computer's accuracy, and insights into quantum mechanical patterns and relationships are found by mining this data. Our quantum devices, like the one I have, only become superconducting at incredibly low temperatures, just below, not below absolute zero, just above absolute zero. That would be an accomplishment. Therefore, they must run inside a special type of refrigerator called a dilution refrigerator. When you make these things cold, it also presents challenges to actually wire the chip in place. But I'm not going to go into that because it's not related to the software. However, needless to say, assuming you've managed to get all the parameters and the pulses correct, then the qubits at this point will actually start responding and performing your computation for you. At Rigetti, we emphasize a special type of quantum computing called classical quantum hybrid computing. So that's where you can do two things. You can perform qubit operations, such as the one I showed you earlier, and you can also perform simple classical operations like if statements mid-program. So in order to run these classical instructions, you need the help of a classical computer. Unfortunately, for trying to develop the software for this, you don't have a lot of time to insert classical instructions in the midst of a quantum program. So, back when I was working at LinkedIn, we were pretty impressed if we got a response time of 20 milliseconds. At Rigetti, though, the quantum programs run in 20 microseconds. And so to insert some sort of classical instructions in the middle of that, you basically need to use FPGAs and other specialized hardware and so forth. To give you some perspective in this, the length of the wires connecting the computer to our FPGAs become relevant at this time scale because of the time it takes for light to travel up and down the wire. So this has led to us to make some pretty major innovations in terms of embedded hardware and software, as well as custom FPGAs and control electronics in order to support this use case. All right, so we're almost done. Now that the quantum program has been executed, the final step is to get the data out, and we call that step readout. Again, we have this analog problem that comes back to bite us, which is that the data that comes out of the computer is continuous, and there's no clear-cut distinction between zeros and ones. There is some inherent inaccuracy in our instruments. That means noisy data can be ambiguous. So in this case, we need to run sort of machine learning-esque algorithms to cluster the data between 0 and 1. In this case, we know that the green state likely represents a 0 qubit in the 0 position, and the orange likely represents 1. But this is less clear-cut in some other cases. So now you can see the full cycle of everything that it takes in order to run a quantum program. Hopefully this has given you some impression of the software challenges that we face in making quantum computers a reality. The quantum computers, the problems that I showed are just sort of scratching the surface of the problems that we encounter today. And one of those problems, and the reason why we're here, is that most of what we have written so far is in Python, which has been a really great language for our physicists and our scientists to use in order to calibrate the computer. The problem is it's not really that fast. And as performance and as classical co-processing becomes more and more important, we're trying to move to something that's more lower level. And we're beginning to, in the nascent stages of writing some of these key components, which we really understand well in Rust. And so my appeal to those here is if you're sort of like me, and you are a software engineer working on enterprise cloud systems, and instead you want to change the nature of how we think about how we think about computing and how we think about information, this is a really good place to go. So with classical computers, an analogy to classical computers is that we're basically where we were about 50 years ago with quantum computers. The first mainframes are coming online. They don't do that much yet. But the hardware is rapidly improving, and people are beginning to recognize that there's enormous potential. And software engineers, particularly software engineers that work for building performance systems, have a really huge role to play in this next step of computing. So, like I said, a year ago I decided that I was no longer content just writing software. I wanted to work on something that advanced our understanding of information and the way we compute with it. And over the last year, that's turned out to be a really great decision. So if you're like me and you're interested in some of the things that you saw here today, please get in touch. You can also visit our website, rigetti.com, where you can try building some quantum programs for yourself. Building a quantum computer requires many different kinds of people with many different backgrounds. Theoretical physicists, mathematicians, and researchers all have an important role to play, but so do software engineers like you and me. So through the creation of new and innovative software, we will hopefully be able to build the world's most powerful computer. So thank you very much for the invite.
Any questions? Someone will catch this? Or I'll just... There you are.
So What I'm wondering as you describe this process is, what does debugging look like? Like, this is the definition of a Heisenbug. Like, you literally cannot inspect the state of the system without changing it. So I guess, but I'm just curious if you have any experience in building these quantum programs, how you debug them when you have problems. Either like, because it's also, either the problem could be I messed up the quantum program, or the pulse is like slightly off. It's like 0.5 instead of 0.6, and now all my distributions are wrong or something. And there's no like QDB that you can use to backtrace it. So I'm just wondering if you could talk about the experience of debugging and what kind of tools you use to try and fix errors in quantum programs.
Yeah, so when someone asks me, is the software you're writing working, the best answer I can give them is maybe. Everything to do with quantum computing is analog, and it's also probabilistic. Like I mentioned, the algorithms that people are writing to run on the quantum computers are guaranteed to give you the correct result at some sort of number of samples, or they're not really guaranteed, but they're guaranteed above a certain threshold or probability. So QA is and testing and debugging is definitely an open problem. We have abstracted away different parts of the software stack. Like I mentioned, the compiler has kind of a clear input-output. The translation layer has clear inputs and outputs. But at the bottom layer, you've got a system that's inherently probabilistic and something that you can never observe during the state of a quantum program. So it's a unique challenge. It's something that we have to live with. And at the end of the day, we just kind of cross our fingers and hope it all comes together.
So how would you test the new intrinsic? Like if you're adding an operation to Quill, like what's the...
Yeah,
I have no idea what that process looks like, right?
Fortunately, our team of physicists, have more access to the quantum computer than you have at the Quill level, which means that when you run an X-gate, for instance, to take the qubit from 0 to 1, the physicists had previously run a ton of experiments, taking millions and millions of pieces of data to try and figure out how close our programs are to actually running from a 0 to a 1. And there are a number of different ways you can kind of look at the qubit from different directions and all these sorts of tricks that you can use to bring up or calibrate the quantum computer to run initially. But we can only guarantee that level of accuracy on kind of 1 and 2 qubit scales, and even that is really, really difficult. So you're kind of trusting us that we've calibrated the system to give the operations that we are advertising, and then it's up to you to then combine those into something that would be novel and we can't actually verify the results of.
How hard is it to book time on the CI machine?
You can email me, and we can give access to people on the quantum computers. They're kind of like the old mainframes where you have to book time and only one person can use it, and it takes up an entire room. But we can definitely do that. So there's my email.
Yeah, my question is, quantum computing right now looks kind of like in-memory computing for like regular digital computers, I guess. Has there been any work on like computing with quantum signals instead of like qubits? Does that question make sense?
Maybe. I might not be the right person to answer it because I don't have a strong physics background, but I will say that there are a number of different approaches to building a quantum computer. The approach that we're taking is the same approach that IBM and Google are taking, but it's not the same approach, for instance, that Microsoft is taking. So we are printing electrical circuits, basically, superconducting electrical circuits onto silicon. Another way that you can build a quantum computer is by trapping an ion, and that becomes your qubit. Microsoft is exploring something completely different, and if you go to one of these quantum computing conferences, you'll find dozens of different ways of building a quantum computer. We think, obviously, our way is the most promising, but all you really need is some way of representing a qubit, some quantum mechanical system that has 2 states and that you can control. Dan works with me, so maybe he's going to answer.
My question is a little bit more hardware. I don't know if this is unneeded complexity, but you said that currently the graph is 2-dimensional. Have you thought about adding more connections or more density to the graph by doing a 3-dimensional circuit?
Yeah, so I obviously can't share our future plans, but I mean, if you think about it, you're eventually going to run out of space in 2 dimensions as you continue to scale out the number of qubits. This week we just announced that we are building a 128 qubit processor within the next year. That article went public yesterday, I hope. So, with 128, you're already running into problems with delivering the signal from various different directions and so forth. So that's definitely a step that people in the industry and in the research community are exploring. Dan.
Hello. I'm Dan. I work with Stephen. I wanted to add just a few more details to some of the questions we already asked. For debugging, we have, if you get the big one, you can simulate up to 35 qubits classically on our quantum virtual machine. And the difference there is when you measure it, it can emulate a quantum computer and destroy most of your information and just give you the result. But it also, because it was emulated, lets you access the wave function directly. So if you're debugging at the algorithm scale and you're not sure if you just put a gate in the wrong place or your logic's wrong, that's something that at least up to 35 qubits gives you full visibility into the system. And many of our users use that first to check that they didn't mess anything up before they get time on the actual computer. And then there was a question about using quantum signals. I think the closest thing to that would be optical quantum computing, which uses nonlinear tricks in light to have qubits, but the qubits are encoded in photons and they're moving. I don't know much about it, but it's one of the dozens or so other ways you could do a quantum computer. And yeah, it's probably the closest to what you were describing.
Other questions?
So, the way you've described the language. So I have some background in physics. I used to do physics, done some quantum computing, and I always as someone also interested in PL, these 2 problems interested me basically. What would be the assembly equivalent for quantum computing, and what would be the Verilog equivalent for quantum computing? Quill seems to be the Verilog equivalent, which is you are programming what the gates will be at a slightly higher level. So you're not programming, the program doesn't run on the computer. The program just puts the computer in a certain state and then pushes stuff through. Do you folks have plans for, do you folks have thoughts about the other one, actually running, how would code running on a quantum computer look like? That probably needs more gates than 128, but or more qubits than 128, but.
Yeah, I mean, quantum programming language is an interesting area of research to explore. It's at some point with classical computers, people got tired of writing assembly, and they moved on to something with a higher level of abstraction. And then we've continued over the last 50 years to move up that chain of abstraction. We're not even close to that yet with quantum computers because we can hardly get the assembly to work. But you can imagine that the next step is probably going to be something like this, coming up with a higher level programming language that at its foundation is working with qubits instead of bits. So I will, if that's all the questions, I will end with another shameless plug for careers at Rigetti. We're specifically looking for a Rust expert to come on, join our team. Otherwise we'll all have to be writing C++, and I don't want to deal with templates all day. So if you are interested, there are 3 of us here from Rigetti Computing, Nicola, Dan, and myself. Please come talk to us afterwards. We obviously love talking about this stuff, in particular the software and the compilation chain and so forth. So thank you so much again for the invite, and enjoy the rest of the meetup.
Next up, we've got Isaac from Dropbox. Where is my mouse? Aha. All right. Hi, everyone. My name's Isaac. Like Manish said, I work at Dropbox. I'm here today to talk about how we use Rust in one area of Dropbox. I'm excited to say that we actually use Rust in quite a few different teams at Dropbox. I know Jamie Turner, some of you might remember, came and gave a talk about a year or two ago about how we were using Rust in some of our backend services. And I work on our desktop client team. We maintain the sync engine in Dropbox. So this is the thing that makes the green check mark appear when all of your files are in sync, backs everything up, syncs everything down. Hopefully it has worked well for you, but we are invested in constantly making it better. While we're making plugs, I figured I would make one plug myself. When I'm not coding, I am a local performer. And if you want to use futures, I am performing in Pirates of Penzance currently. And it's coming to San Francisco next weekend. So let me know if you're interested. But anyways, back to the story at hand here. So sync is pretty interesting in a lot of ways. And before I go into how we're using Rust, why it is uniquely helping us test our product and make sure it's doing the right thing, I just wanted to present a few of the things that make it an interesting problem. So first, sync is a distributed systems problem, and it is a unique one in that sense. So on the left here, this is like a very simple log of activity that might happen on the Dropbox server. Maybe you first add foo.txt, then you add a folder, and then you add a file within it. And in a very straightforward solution to this problem, we would just replay the remote journal of operations onto the local client, and then you would be synced. But running on someone's actual system, it's not quite that simple. A lot of things can get in our way. For example, maybe we just don't have access to write to that one file or something like that. So in this case, we actually need to support partial orders and more complex transformations on the information that the server has. But the complexities are not just in the distributed systems world. The actual installation location of the desktop client is also pretty problematic. So some users have Dropbox in some super bizarre location on some operating system we've never heard of, running on some file system that has bizarre properties. Maybe their hardware doesn't even work right. We see random users' laptops flipping bits all the time, and then we have to be defensive against that to make sure Dropbox doesn't screw up their data or propagate issues with their machine to other people's machines. And similarly, because it's desktop software, we're completely at the user's mercy and have to be able to live in an environment where we really don't control anything. So I'm sure the Firefox devs in the room are probably very familiar with this. But desktop software is really interesting in this regard. There's all sorts of crazy other applications running on the system. Operating system updates come out and totally break your assumptions. The permission error, like I mentioned before, if a user just has locked us out of some area, we need to be robust to that. So there are a lot of challenges. That's sort of a long way of saying it's really important that we can encode the invariants we care about very explicitly and be as defensive as possible. I thought it was interesting that the previous talk also talked about migrating from Python to Rust, because Dropbox has been on a similar journey in some of our systems. So the sync engine at Dropbox for a long time was written entirely in entirely in Python. The first kernels of it were popping up in 10 years ago, and it wasn't really built to support a lot of both the features that Dropbox now supports, right? Our product itself has changed pretty dramatically over the years. And it wasn't really built with the current state of cloud files in mind, just in terms of platforms that we're running on, number of users, number of files, things like that. So Rust came into the picture. Previously at Dropbox, we
had the pleasure of using Rust in one of our backend systems that managed some of our storage. And I think this was actually even before Rust 1.0, so it was like kind of dicey at times. People weren't sure if it was a good bet, but it's really paid off. I think everyone's really happy with it. And we've sort of doubled down internally and have started building more and more systems in Rust. So I won't go into too much more detail about like why we're rewriting the system. It sort of boils down to just there were a lot of architectural decisions that we would like to rectify, and while we're in the process of doing so, we want to build this in a system that can support a much bigger team, iterating quickly, while still having high confidence that what we're building is correct, that when we ship it out to hundreds of millions of users every week, that we're not going to blow away all their files or anything like that. And specifically, the subject of this talk is we want this new system to be really testable from day one. And so when we were selecting Rust and looking at different languages, this was a question we kept coming back to, of what would a fairly sophisticated testing system look like, and how cleanly and elegantly would that fit into the overall design of the system. So I want to give a brief overview of how features work in Rust. How many of you are familiar with features in Rust? Okay. So about half. So a lot of things here. There probably are other people in the room that can answer better than I. I was completely new to this as well about a year ago. But it's a really interesting paradigm, different from other languages I'd worked in, and is pretty core to the testability of the new sync engine that Dropbox has been working on. So the first interesting thing about Rust features model is people describe it as a a readiness-based features model instead of completion-based. And so what this means is instead of, if you have some feature that you're interested in and you want to get the result, in a traditional completion-based approach, you will get some notification, your function will get called with the result when it's done. So you're kind of like, you ignore the feature while it's running, and then eventually you get some callback with the result. In a readiness-based approach, which is the direction Rust has gone in, you as sort of the owner of the feature are responsible for driving that feature forward, and you will receive a notification when it is appropriate to try to drive the feature forward. But it's up to you then to keep pushing for progress, and then eventually when the feature is done, it will give you the result directly. So it's sort of turned upside down a little bit. So this is the Rust trait as it's defined today, I think. It's actually been changing quite a bit, so I think the version that we're using in our code is a little dated. And even this, I think I've simplified a little bit. So anything that is a feature in Rust needs to define some output. Makes sense. Some features can error, in which case you would return a result of some object, or not. And then you also implement a poll function. And this is the function that basically is intended to drive the feature forward. And if the feature is now complete, it will return async ready. And if the feature is not complete, it returns pending. The interesting piece here is that if the feature is not complete, someone needs to know in the future to check if that feature has resolved in the future. Someone needs to check down the road if that feature has resolved. So you pass in a task to the poll function, and this is basically just the thing that you're registering to be the recipient of a notification when you should call poll again. So you call this feature, you call poll. If it returns pending, you kind of go back to sleep. Eventually, that task is going to receive a notification on it. And when it does, that means you need to call poll again on the feature to either see if it's done now or drive further progress. And so in a super simple case, if you have a feature that you just want to wait until it's done, internally you basically have a while loop. You're not just calling loop or you're not just calling poll like in a tight loop, because, for example, internally the feature might be blocked on stuff that's happening off thread, or that would not be resolved by just like continuously calling poll. But you will set up some tasks such that you can go to sleep on a condition variable, and then when that task gets a notification, you can call poll again, and then eventually your feature will get resolved. Any questions on that right now? Cool. Yeah, also happy to take questions at any time if things do come up. Okay, so that's sort of like futures in a nutshell in Rust. So with the sync engine, what we've done is represent the entire application essentially as one big future. The idea that the sync engine is itself just a composition of many futures is not really a departure from how futures in Rust work generally. For example, if I have one future and I want to join it with another future, I call join on the first future, pass in the new one, and both are consumed in order to build a new future. And that's kind of like the wrapper. So they're now composed inside. And so the sync engine is sort of, in our usage, is following that paradigm. We think of, in our focus on testability from the beginning, we knew that we wanted to end up with a system that can be, at the end of the day, serialized all on one thread. So in order to do testing in a reproducible manner, we didn't want to have to deal with basically being at the mercy of like the operating system scheduling when we're trying to reproduce exactly what happened for a given execution. So here's a little bit what it looks like at the top level of the sync engine future. So we're implementing future, but all we're doing internally is basically polling a bunch of other futures. And these futures are kind of unique in that they don't error, and they actually also don't ever complete anything. So they just drive progress forward in like their particular area. And that gives sort of like a lightweight thread feeling. We basically, within the sync engine, have all of these different components. So there's this one component that's responsible for downloading updates from Dropbox.com. There's another component that's responsible for figuring out when things on disk have changed. But at the end of the day, they are all serialized onto the main thread. And what that means is that we don't have to deal with any OS wake-ups or concurrency challenges in that regard. It's completely cooperative. So once we allow the remote events worker to pull, it's going to make a little bit of progress and then yield. And it's up to that component to do so. And that's sort of the futures model in Rust. You implement pull. It's supposed to be snappy. You shouldn't do any blocking work in there. It's just designed to make a little bit more progress and then yield back as soon as you can. So we pull each of these lightweight threads, and then at the end, we check if we're synced by doing some queries. I've simplified it here, in which case the overall, like this big wrapper future will return, and then great, we're done. Otherwise, we return that we're not ready, and that means that like the usual contract must be upheld. So if we return not ready, either a notification has already been registered on the task, in which case another pull call will cause us to make progress, or down the road, once some I/O or something like that gets back, then the notification will get registered. One thing that's a little interesting here is that everything's running on one thread, but there are dependencies across these different components. For example, on the right side of the screen, we have what I call the scheduler. And the scheduler's job is to look at the current state of the world. So what the sync engine thinks is currently on disk and what the sync engine thinks the server currently looks like, and say, okay, I want to delete a file. Like that's the next step we need to take in order to converge the two trees. And so in order to do that, it'll spawn some task. Here I called it the apply remote delete task to actually delete something from disk. But in order to delete something from disk, we first need to actually open that thing on disk and then fstat it to verify that the thing on disk actually hasn't changed, right? We don't want to miss a user edit or something like that, and just blow it away without realizing. In this case, we'll actually call a function on the FS manager, which will give us back a future. And then that component, its poll finishes. And then the FS manager, next time it's polled, is going to say, oh, I have like a new message that's come in. And this request wants to open some file or wants to fstat a file. It might then delegate to a different thread entirely, some worker pool, so that the actual I/O is not happening on the main thread. And then when that result comes back, it'll satisfy the internal future, which then satisfies the future that the scheduler is blocked on. All right, so now going into exactly like how we test a system like this. So obviously, if we're rewriting the sync engine, we need to be really pretty sure that it's more correct than the existing one. And the specific class of bugs that we're most concerned in with something like this are many different categories of races. So one of these categories is what I was describing before, where we get some instruction to delete a file from Dropbox.com, but before we can actually delete it, the user has changed it locally. So ideally, in the green, we detect that change and do not delete the file. But what if our code doesn't have handling for that race? We just assume, oh, if we learned about a delete, probably user hasn't changed the file, let's just like blow it away. So that would be bad. We want to make sure our test system can push us into those places such that we can detect an error. Similarly, we need to be crash safe at any moment, right? We're running desktop software on someone's machine, the battery might die, they might just kill Dropbox because it's taking up too much memory. And no matter like what we're trying to do at any time, we need to be robust to that. So if we're in the middle of this disk operation, we need to be able to handle that. If we've made some requests to the network, we need to know that we might never receive the response to that network request because we might have been killed. So yeah, and I mean, this probably is no surprise to anyone. It's really hard to think about even like generate these issues to begin with. Like if you're writing a diff, it's hard to even proactively think about all the races that can occur. And even if you can think about it, it's pretty hard to like put your code in such a position that you are testing this exact race to begin with. And if you get a report anecdotally, well, it's probably not as bad as the true Heisen bugs, but it's close. So when we're building the system, we want it to be easy for developers to track down changes. And one piece of this is that it needs to be 100% reproducible. We have other test systems at Dropbox that aren't 100% reproducible. And they do find lots of interesting issues, but it is a huge pain to figure out what happened. I know if usually the flow is something like, oh, like CI found some failure over the weekend, and you look through the logs and it doesn't totally make sense. And you just really wish there was one more log line added at the right place, but it's not there. So you add it in, and then you never see the bug again. So that's something we really wanted to avoid with this system. We want people to be able to hit errors that CI finds just through the mindless millions of random runs, and be able to super trivially just reproduce that exact run locally. That way they can run it in a debugger themselves. They can add print lines and figure out exactly what happened. So that's goal number one. Goal number two is we want this test system to cover all of those races that we were talking about sort of automatically. At any point where we're yielding, where basically we're doing some I/O operation and we're waiting, that is a point for something to go wrong that the code may or may not have handled. So the goal is basically to inject reorder events and inject crashes and errors randomly at all of these possible locations without necessarily having to mark every single one of those in the code as a possible failure point. And this is something that Rust and Futures has made really, really, really easy. Okay, so how do we do this first bit, this concurrency / reordering issue? How do we make sure that in all of the places where we yield, we are stressing the system in an appropriate manner? So what we do is all the I/O is mocked out, which lets us serialize it in some random order. So this means that we've actually implemented a mock backend implementation that just runs in process on the same machine. That's sort of a simplified version of the protocol that the client speaks with the server. And we've implemented a mock Rust implementation of the local file system. It's not super complicated, doesn't have all the bells and whistles of a real file system, but we ensure that our tests that we run against all our platform implementations also pass against this in-memory one. So it should have all the same invariants that we expect. So then we take these implementations and we wrap them with another implementation of the same trait. So we can sort of parameterize the entire system to allow us to pick and choose whether we're running with one of these mocks that can have all these reorderings or not. And any request that comes in, we first send to what we call a driver. So in this example, I know it's a little small, but what we're doing is we're wrapping our thread pool. So the thread pool here has a super simple trait. All it does is hash a vec of data, and it gives you back the hash of that data. And it cannot error. So the first thing, whereas normally you would just call hash, and then you wait for the thread pool, and eventually that feature will be resolved. Instead, first we call request on the driver, and we pass it a closure of what we will want to do later. So you'll see this when we go through the pseudocode for like what this test harness looks like. But what this does is it allows the test harness to basically say, okay, I have all these requests outstanding. Let me choose a random one and actually run that request. And it doesn't even have to deliver the response, the result of that. It can just like resolve the feature but not yet deliver it, then resolve something else, try all the different orderings. And then later it can actually satisfy the original request with the resolved information. And then in this case, there's nothing to error because the trait itself cannot error. But if we were working with like the real file system or making a network request or something, these are all opportunities for automatically, putting in a 500 or putting in some like file system I/O error or just like random errors like that. And we'll come back to this a little bit once we see the full pseudocode for the run loop. Okay, so that's how we're going to attack making sure we get this concurrency testing. From a determinism perspective, we use a quantum computer to generate a random number. Not yet. But yeah, so at the beginning of the test, we initialize some random number generator. And this is the thing that lets our test be really easily portable and reproducible. So if the test is just running for the first time, it'll generate its own random seed and run from there just off that one seed. But if you want to reproduce some crazy failure, it ran in CI for multiple minutes, thousands of operations, ridiculous interleavings, crashes, blah, 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 blah. All you need to do to run that on your own local machine is just cargo run the seed, and everything will happen exactly from there. If the test harness being deterministic is great because it has to make a lot of decisions like initializing the file system with random information, initializing your Dropbox on Dropbox.com with random data. But it's pretty worthless if the actual engine itself, the future that we are driving, is not deterministic itself. And I was actually pretty surprised at how doable this really was. And I would encourage everyone else to try this as well. It's really not that hard to remove non-determinism entirely from your whole application. In this case, we really only ran into a couple small issues. One was we didn't realize that the Rust standard library's collections by default have some non-determinism built in for DDoS prevention. So the hash maps themselves are seeded with some additional random information. And so that was, of course, throwing off all the determinism in our tests. So what we do is we wrap those standard collections with our own variant that does not have that kind of randomness. Obviously, it's running on someone's personal computer, so if they want to DDoS themselves and sync their files super slow, like they are welcome to do so. And it also is really valuable having a test harness that can assert that things really are deterministic is really valuable. We would just run every single test twice, and capture a lot of a lot of signals about the run to verify that things happen exactly as they both times. For example, what the final state of the disk is, what the sequence of operations were, how many polls, like the exact number it took, things like that. So once we had that in place, it was pretty easy to go through and just like track down divergences in the program. Like you can take 2 logs, say like, oh, that's weird. It was the same up until line 60,000. And then you'll see, oh yeah, here we're sorting by this thing that came out of a hash map, not a DBX map, or So this really changed the debugging game for us. Like we kind of live by these tools now. We just like send it out to CI, see what failures it finds. When they come back, we just run them locally, can debug things from there. All right, so this is the exciting part. So what does the actual like run loop for this testing system look like? So this is simplified to fit on one screen. So a lot of stuff is elided, but first we initialize this random number generator, like I said. Then we set up the initial state of the disk and the remote state in Dropbox. Then we instantiate the sync engine itself. So here again, this is the future. And in like a normal, if this were just deployed to your computer and you wanted it to sync files, you could just do .wait, and then it'll do the right thing. In this case, because poll is sort of the unit of abstraction, it's a perfect place for us to get in the middle and muck around with exactly what's happening to test these kinds of races. So just like with this kind of simple form where we just poll the engine until it's synced, and then at the end we run some consistency checks, it's pretty valuable in and of itself. We'll be able to know that we don't panic in quite a large number of environments or scenarios. We know we eventually terminate. And we know that all of the work that we thought was concurrent is actually safe to be concurrent. And so what I mean by that is all of the asynchronous operations in the system are being caught by this driver, and then we're choosing random ones to run at the same time, or rather choosing random ones to run in a random serialized order. At the end of the day, everything's running on this single main test thread. So going back to that example we were looking at before, if the top level future is polling the scheduler and the scheduler decides, oh, I need to do some operation that needs to read from disk, when that future actually tries to run, it first is going to defer to the driver, and it's just going to block until the driver says, oh yeah, like I'm going to satisfy that one to move forward. Okay, so the other thing we do is what we call futzing. So while the test is running, in addition to the sync engine, while the sync engine is trying to converge the two states, we are acting as like a nefarious user or other users in your Dropbox shared folders, things like that, to basically make it harder for the sync engine to reach, to reconcile the states, and setting us up for hitting all of these races that we're worried about. So we might randomly decide to screw around with the disk, swap files, do really tricky things like take a child of a folder and make it the parent of that file. All of those, like the worst possible things imaginable that a user could be doing to a sync engine, we will do them here. And here, I mean, anything you can imagine are the things that we will be doing at this stage. One thing that's interesting is, and we weren't really sure how to solve this at first, was like, how do we make sure this test actually completes at some point? Because if the sync engine is constantly trying to sync, and we're constantly like making it unsynced, the test is never going to complete. So this simple solution we came up with was just to do so with a decaying probability. So the longer the test goes on, the lower and lower chance that we'll keep messing with the file system and the server. At which point, at some point, the two should, not be changing anymore, and then the sync engine should be able to reach a sync state between the two. So in addition to reaching a sync state, you really need to assert a few more things before you know your sync engine is actually doing something good. For example, we could just delete all the files, delete everything from Dropbox on the server, delete everything locally, and like, great, we're synced. So we need to make sure that's not what happened. So additionally, at the end, we assert a bunch of invariants to make sure that things reach a synced state and did so according to a few set of rules. It's important here we found to keep these rules minimal, but still as comprehensive as possible. So we don't want to write another sync engine to verify that the rules are valid. But there are a lot of like super trivial things that you can assert and get a big bang for your buck. So for example, at the end of a run, we'll verify that our representation of the user's file system, so effectively like a cached view, indeed matches the user's file system at the end. This means that we haven't missed any local changes, and we'll do the same thing remotely. Similarly, if we added files during the test run, we should assert that those files didn't, mysteriously disappear. Things like that. One thing that's kind of fun about this particular setup using the poll abstraction to run this testing system is that we can verify that we don't deadlock, that we haven't missed a notification somewhere in the stack. Because the invariant when you poll a future is that it's either done or it's not done and a notification is already registered, in which case you should poll again, or a notification will be registered at some point in the future. But in this case, the only person who can be satisfying work is the driver. So if the driver's empty, meaning like we haven't received any requests, and there's no notification registered, then that means somewhere we actually just like dropped a notification, and like our futures implementations internally are inconsistent. And so this has actually also caught a bunch of bugs. For the most part, as much as we can, we try to avoid implementing poll ourselves and like implementing our own features in favor of just using async await and the existing channels and things like that. But we have implemented quite a few things ourselves, and it's easy to get those details wrong, and this will catch things like that. So getting towards the end, I just wanted to share one kind of fun. This is like way too small, so I will just describe it. But this is one really fun bug that we caught very early on when we were building the system that kind of gave us faith that it was not a waste of time. In this case, we aren't testing, the bug in the end wasn't so much a race as just a logic error where we didn't consider a certain situation that this test harness was able to put us in by basically setting things up randomly. So the issue here, we're trying to upload blocks of data to the server. So every file that comes in a Dropbox, we'll split into blocks and then we'll upload them. The first step of that process, the server tells us which blocks it needs, because it might not need all of them. So what we were doing on the left is we're iterating over all the blocks in the file. Then we're filtering out the ones the server doesn't need. Then we're calling enumerate to get the index of the block in the file so that we know where to actually, like what offset to read on disk from. The change was to flip the enumerate and the filter line, where we're filtering the server ones. I know it's small. Can anyone see why that might be the issue? Yeah, exactly. We were just getting the wrong indices before because we were filtering and then enumerating. So the offsets into the file were just completely wrong, but only if the blocks that the server already had were in the middle of the file. And sure enough, we had a unit test, at the end of the. So it was only wrong. Yeah, if the blocks that the server had were not at the end of the file. And sure enough, we randomly had the one unit test we had was just the last block in the file that it didn't need to upload, so we didn't catch it. And that's like a human mistake. We probably should have thought about this in code review, but this kind of system was able to eventually, it panics because in our implementation of our backend, we expected some block, we rehashed it, didn't match, and so we were able to fix it. And don't worry, the real Dropbox server also validates that, so this wouldn't have caused too many problems. So just a couple closing thoughts. In this presentation, I was mostly talking about the instance of this test harness where the network and the file system are mocked out. But we also have variants of this that actually use real ones of both and are fully deterministic. It's a lot more challenging to do that once you start using a real server backend, like the sprawling web of all of Dropbox, and when you have like a real file system disk, because now you have all of these sources of non-determinism that you don't control. So for example, inodes are something that like the sync engine needs to use and manipulate. It puts them in data structures that at some point get sorted and things like that. But that's now a source of non-determinism once we're using a real file system. So to do this required building translation layers to basically take non-deterministic information and making it input it into the system in the exact same representation every time. And it's a lot slower. So talking to like the real Dropbox, or at least a VM running all of the Dropbox services required, of course, does not allow us to run at quite the speed that we run this one. And so the number of random test cases you can run really benefits from having it just all be in one process, all Rust, end to end. So yeah, thanks a lot for having me. I'm happy to take some questions. Yeah. Thanks.
Fantastic talk. Thank you very much. My question is, do you use CRDTs? And if not, why not?
I'm not familiar with that.
CRDTs are conflict-free replicated data types, which are used to merge data structures when you have partitions.
So I'm not sure. I have enough of an understanding of that area to say. I know, for example, like other products that Dropbox uses, for example, like our paper products, which sort of does like live editing, has a completely different syncing stack from our like traditional file sync system, and that one is more based on operational transforms and things like that. In terms of the actual file sync, I would suspect no. I don't know if anyone else, a couple other Dropboxes here could comment.
Things look a lot like CRDs. Okay. I don't know if they fully formally are.
I guess, very quickly, what file system do you use on your servers online? Is it just an ext3 or something?
Yeah, it's X3, I assume, Ubuntu. I don't know for sure.
Do you mean for storage or like on the application servers?
On the storage.
Oh, the storage nodes themselves. I don't know. Do you know, Aaron?
I mean, it's all our own data structures, and it's in a database. Like, the metadata is on the database. The data is kept in our own system that we built from scratch. We just access the devices directly, just as raw block devices.
Thank you.
There are very good blog posts on the engineering blog.
So it seems like what the tests try to get at is there's some like temporal state machine that underlies the thing you'd like to describe about how conflicts should be treated when they occur and like what should happen when this particular sequence of events happens. And I'm curious, and this process of like stochastic test generation is one way of asking, does my code match the state machine that we'd like to have? But another way would be, a more formal way would be if you could formally specify the state machine and then try to encode that somehow, like either in the type system of Rust or have some method of saying, given a complete specification of the state machine, can we ask if this Rust code satisfies that? So I guess the question there is, do y'all have a more formal specification of the state? Like how implicit versus explicit is it? And have y'all explored any methods beyond just test generation for trying to check if your code fulfills that sort of guarantee?
Yeah. So it's a great question. The system itself is sort of separated into two pieces. One is sort of the theoretical planning layer that basically is taking these inputs of what is the current state of the world and what are the appropriate steps to get there. And then there are the pieces of the system that are just responsible for basically getting consistent views of the server or the file system so that we can then make these kind of algorithmic decisions about what direction to go in. So this piece, what I was talking about here, is mostly geared at the latter. So basically testing these systems that have to deal with like the raciness of the network or the file system, and less about testing the We've actually talked, in terms of testing that area more rigorously, there are a couple folks at Dropbox who have looked at doing more sort of like proof-oriented development in these areas. We haven't adopted that in any significant way in the sync engine today. But yeah.
It looks like you guys have a relatively non-trivial amount of future code at this point. What is your guys' thoughts around future 0.3 with async await, that sort of transition you're going through, as well as how have you felt with onboarding people to the combinatoric style of futures?
Yeah. So I think early on, we were sort of just willing to deal with the combinators because we knew one day salvation would be here and we would have async await style. Someone actually on our team, unfortunately is not here, just on top of generators implemented his own macro solution for async await that we actually currently use today. So we've gone through and migrated the vast majority of the code base away from combinators just to await as is, and it's great. Like overnight, I think, especially for new folks on the team, it was like night and day, just in terms of making the code readable and easier to like iterate on. We're very excited about being able to the pinning for. How did you do that without pinning? Right. So we don't have pinning currently. So references that are used like across the yields, we will clone. Okay. Yeah. And that doesn't happen in like all contexts, but in many cases. Some of like the resources that we're using were already shared, already RC'd or something like that, in which case we could just pretty easily make use of that. But yeah, being able to remove all of that and have like pinning first class will be pretty awesome. So.
This is sort of a specific question about how you wrote that like ginormous future that has all those sub-futures. Yeah. So I don't know like if that's more pseudocodey or more not pseudocodey. Yeah, that one. Mm-hmm. So like all of those futures, the 5 futures that you're pulling first, do those futures never return? Like those futures never will resolve, and so they wouldn't be usable like separately, not in this like special future that has a separate sync.
Yeah, that's gotcha. Right. So their type actually is like item bang, error bang.
Gotcha.
And that is sort of unique at the top level where we have these, what we really think of as lightweight threads. They're kind of just these things that run forever until the engine is shut down. Then within those, it becomes a little more traditional where there's some data structure tracking real futures that are returning results and errors, things like that.
Gotcha. Very cool. Thank you.
Hi. Can I ask, how weird is your Rust code? I ask this because, like there's only a couple of really large open source Rust code bases, and many people with opinions on the internet, who are very rare, have lots of things to say and guess at like the terminal state of large Rust projects, especially, people love to speculate about what happens in private organizations when no one has to look at the code. And so I'm curious, like, what do you do around panic unwinding versus panic equals abort? Do you have weird constraints around out of memory? Do you lint unsafe? Do you have some extra out of band processes for these? Do you have like bizarre build.rses that would make us cry? Like, what does it look like to run it as like a practical software project in the org?
That's a good question. I mean, we should probably talk for a more extensive answer than this one. Trying to think where to begin. So I am relatively new to Rust myself. This is basically the first project that I worked on in Rust. And that's true for, there's probably about, 15 to 20 folks who work in the area now. And almost everyone on the team, their first exposure to Rust is this. So for a lot of the people on the team, no matter how weird it is, they just think that's Rust, for better or for worse. I think we do have a couple, like 2 to 3 folks on the team who actually have been really involved. They've submitted a lot of patches back to Rust upstream, and been involved in some of the compiler work, things like that. And so I think they've done a pretty good job of steering us into like, that's wrong, this is right. But I also don't know a lot of folks that like have this kind of wacky thing going on that we thought was pretty cool. So yeah, I don't know. Overall though, like just if I came into it sort of like language agnostically, if I looked at this, it looks very reasonable to me. I'm really happy with where we are. And like people are able to ramp up on it relatively reasonably. But yeah, we should chat more.
Yeah, I think everyone in the community would appreciate that. And I had one quick follow-up question, which I'm speaking to the microphone even it's not on, which is, so this lightweight threading model is like, there are some projects on crates.io that do like analogous or similar things. I think like the most relevant thing that is exciting right now is Actix, which everything is a future, but you don't ever pull them, and they have a mailbox, and all communication is asynchronous.
Yep.
So could you and there's Miyoko, and there's a lot of people have experimented with ways to do this sort of thing on top of futures, and most of them have died because it's experimental. So like, could you contrast your learnings, your implementation, and what you've learned from it with what you might have seen in the open source world?
So I have not seen a ton. Don't have a ton of exposure to some of like the nascent / abandoned external approaches to this. We have, I think, because when we started, a lot of the future stuff was pretty early, and we were, even simple things of just like channels that aren't send, or like, just, kind of like basic things we ended up having to implement ourselves in the beginning. And so we have always leaned on the side of trying to keep it as simple as possible so that there's not as much boilerplate to like learn all at once. It's possible that now there is some third-party alternative that like we could adapt this to, but I haven't seen enough to really say either way. Yeah. I don't know where the. I should also say there have been other like core Rust folks who have helped us quite a bit actually. Alex Crichton in particular, I know he's up in Seattle now. He helped us a lot with some of the stuff early on. We were like, is this insane? And he was like, no, that actually makes a lot of sense. And we were like, okay, like we won't regret this forever.
So does your sync engine have to deal with exactly once semantics?
Exactly once semantics?
Yes.
I mean, the key is the real challenge is that we need to be, whether we're talking to the server or talking to the local disk, it needs to be fully transactional. And so we don't actually have that guarantee traditionally, right? Like if we've taken some operation on the local file system, when we come back, we need to know exactly did it occur or did it not.
Okay, thank you.
So you're using futures, but one of the things you commented about was I/O is done in background threads. So can you elaborate more on that?
Yeah, so basically everything runs on one control thread except for the I/O. So all the file system work, any additional like CPU activity we have to do, like hashing, things like that, that's all deferred to actually other threads. And the futures on the main control thread are basically blocked waiting for those to complete. And so the main control thread will wake up once those values are back.
So you don't use something like Tokyo for managing.
Oh yeah.
Those.
So on the network side internally, there's no thread pool for the network traffic. I'm trying to remember what the name of the Carl's library is they were using. I think H2 is built on top. Yeah. But for example, for the like local file system work, there aren't async I/O interfaces that we can use. So that just runs on traditional threads.
Right. Thank you.
Oh. Yeah. Yeah, exactly. Someone has a thread pool somewhere. Yeah. Yeah.
So with single thread actually processing the state of the system, it becomes critical to not block it And how do you check that like the system is not staling itself? Because basically the model you chose is polling, which is like unlike pushing, where you combine your logic like on the state that someone will eventually call something. You like have to push the work. Like, how do you verify that it's correct?
Yeah. So I mean, just in terms of performance, one thing we actually haven't done, but it's sort of been on our list to do, is add more telemetry into the throughput of these poll calls we're getting. Like if we're hitting some pattern where every 5 minutes, one of the poll call actually blocks for like 30 seconds, that would be pretty damaging, especially since, the system doesn't go anywhere unless this poll is running.
Exactly, yeah.
So, when we're satisfying user requests, like if a user clicks on Dropbox and has to query something in the sync engine, that needs to get into some queue, sync engine needs to get polled, needs to respond to that event and send it out pretty quickly. It's a good question. I think the main way we'll probably fight it is through that kind of monitoring, like just detecting the latency of those requests. One other piece we've done is, because it is a tree of futures, for anything that is sort of like variable number of futures, you ideally don't want to be polling all of those futures every time any one of them wakes up. So like at some point in the tree when a poll comes in, you would like to be able to route it a little more directly than just to all of the things that could possibly need that notification.
Yeah.
So we've implemented like a future map and a future set that internally are actually, it's maintaining its own tasks for all of the futures that are outstanding, so that when those make progress, we sort of can funnel that notification like directly down the tree, so log n down the height of the tree instead of spanning out to every task that's in flight. But for things like these 6 things, it's cheap enough to just go through them.
Yeah, I think you reinvented ePoll inside your
yeah, exactly.
I had another question. Yeah, but I can give it to someone in the meantime.
So what about? So you were saying about reducing non-determinism, and what about time?
What about type?
Time.
Oh, time. Time in what sense? Like performance?
No, in determinism, because time is kind of
Oh.
major contributor
Right.
in non-deterministic behavior.
Yeah. Right. So like backoffs, for example, right? The sync engine, when it hits some error on disk, the normal behaviors will indicate to the user, oh, this file can't be synced right now because permission denied, and we will back off 30 seconds, then a minute or whatever, before we reattempt. But in these tests, if we hit that case, we don't want to just stick around for 30 seconds. So basically everywhere in the system, we try to ever rely on, we try to ever query, we try to make any decisions based on relative time. What we'll do is we'll create a future saying, oh, okay, I want to back off for 30 seconds. And we will just trust that once that future has resolved, 30 seconds have gone by. The nice thing about this is that then our test framework doesn't need to know about time. It can just resolve futures that actually have some notion of time encoded in them, but it will just resolve them and the rest of the system kind of moves forward.
So do you not store timestamps and structs in this system at all?
We do store timestamps, it's important to know, so going back to that first example where we're trying to delete something from disk and we want to know, has the user actually changed it? So the main way we're able to detect that change is through the metadata on the file system, the M time of the file, the inodes, size. So we do record that in our data structures. And the test runner itself, when it is futzing or screwing around with the file system, it will make sure to adjust those in such a way that it matches the standard we hold a regular change to. So for example, if we edit a file as the test runner, we will bump its M time by 1 second, although it's like a meaningless kind of opaque number at that point. But yeah.
Thanks. So writing tests for the system, do you use standard testing framework that, I'm not even sure what the name is, but Cargo is able to run the tests on it? they use that, or do you have some custom one? Because like it seems that it's very a lot of similar tests can occur here, just like by flipping one of the conditions, like in the inputs, and those are regularly easier to write as like BDD rather than like regular.
Right. So each of like the simulations that run in this are not run under cargo tests. Is that what you're asking?
Yeah.
They're actually run with their own binary. So like the test harness is its own application that it sort of depends on the sync engine itself. It instantiates it from there and then sets up all these random inputs, does one test run, and then terminates. For all of our other non-randomized tests, like the hard-coded unit tests or integration tests, things like that, those all run in cargo test.
Okay.
Have you looked at is it even relevant for this type of framework to do test case reduction, like quick check or prop test or something similar?
Yeah, it's a great question. So we have another randomized testing system that specifically targets the algorithmic part that there was a question about before. So the part of the system that, given some input state of the world, proving empirically to ourselves that we can actually reach a synced state. That system, we actually did implement some reduction. So we set up some initial state of the world. If we panic or we hit some invariant breakage, we will say drop one node from the disk and run the whole test again and see if it still happens. That one, it's really kind of, it lends itself to this because there's very clear input and output. Like the input is initial state of the world and output is did it succeed? This one's really tricky to do minimization because there's no clear input because all of the steps we take along the way, we got there basically by random chance. So it's hard, taking out one step would unravel the entire remainder of the test. But we have been thinking about it. Like you can imagine, instead of just going by the seed from the very beginning, printing out like a tape of all the actions that were ever taken so that it's at least well known. And then as we start like removing different actions, we could maybe see that, oh yeah, that one actually doesn't change the final outcome.
So then maybe I was misunderstanding you when you said serialized earlier. You meant it like only in the distributed system sense, not in the SERDI sense. Like you don't actually literally take every poll call.
That's right.
Okay.
Exactly, yeah. We hope we're taking a lot of them as we do randomly explore in these runs, but that's right. Yeah.
All right, thank you. We can still, I think, stick around for a bit. If anyone wants to speak at the next, I think September's all set, but for October, if anyone wants to speak, let me know, or just comment on the meetup later. Thank you.
I want to know how you are auditing third-party licenses.
Aha!
I'm still stuck with
Auditing their licenses or auditing the correct
correct licenses.